Heat pumps are one of the best tools we have for getting homes off gas. But for most households, the single biggest thing standing in the way isn't the pump at all. It's finding somewhere to put the hot water tank that has to come with it. But a company in Scotland thinks it has made that tank disappear. Sunamp, an Edinburgh area firm spun out of university research, has built a heat battery that stores hot water energy in a salt that melts and freezes. It packs the same heat into a box up to 4 times smaller than the cylinder it replaces, with no standing heat loss and no annual safety check. We are going to get inside one of these batteries, work out how a block of salt delivers a full pressure shower, and whether it really is the future of hot water storage. Hot water is a bigger slice of a home's energy than most people realise. In the UK, it runs to around 17% of domestic energy use and more than a fifth of the gas a household burns, almost all of it concentrated into a few short windows each morning and evening. As homes get better insulated and space heating demand falls, that hot water share only grows in importance, which is why the appliance that stores it matters more than it used to. And the appliance most homes have relied on, the insulated hot water cylinder, is quietly wasteful in a way you never see on a bill. A standard tank bleeds somewhere between 1.3 and 3.3 kilowatt hours of heat a day straight into the cupboard around it, just keeping 50 or 60 gallons warm for the moment you want them. Over a year, that adds up to between 500 and 1200 kilowatt hours per household that you paid to generate and never used. For anyone already struggling with energy costs, that loss lands hardest. But the bigger problem with the cylinder is simply where it has to go. Around 80% of British homes run a combi boiler, which makes hot water on demand and needs no tank at all, so those homes have no cupboard set aside for one. The moment you try to fit a heat pump, that changes. A heat pump cannot heat water instantly the way a gas flame does and has to store it, which means finding room for a tank of 50 to 80 gallons. In a flat, a row house, or an older building with no obvious space, there is often nowhere to put it. That single spatial problem is now documented as the biggest physical barrier to getting a heat pump into an existing home. Space, waste, and the friction of fitting a tank where none was ever planned are exactly the problems Sunamp set out to solve. The company was co-founded back in 2005 by the technology entrepreneur Andrew Bissell and Susan Lang Bissell. Bissell had built and sold a medical imaging firm, then went looking for a science problem worth commercializing. In 2008, a Scottish brokerage scheme paired him with Professor Colin Pulham, head of chemistry at the University of Edinburgh. That partnership, funded through research grants and a string of doctoral projects, is where the actual breakthrough came from. What they built is a heat battery, and the idea behind it is one you have already held in your hand. Inside the unit is a salt called sodium acetate trihydrate, the same material in a reusable pocket hand warmer, which Sunamp has refined into a product line it calls Plentigrade. When you charge the battery, you heat that salt until it melts at 277 degrees Fahrenheit. As it melts, it soaks up a large amount of energy without getting any hotter, the same way melting ice holds its temperature while it absorbs heat. The energy goes into changing the salt from solid to liquid rather than into raising its temperature, and that is the trick that lets it store so much in so little space. To get the heat back out, cold mains water is pushed through a high-power heat exchanger buried in the melted salt. As the water draws warmth off the metal, the salt crystallizes back into a solid and releases its stored energy at a steady 277 degrees Fahrenheit, handing you instant, full pressure, hot water at the tap. Because the energy is locked in that melt and freeze change rather than in a large warm volume, the battery holds up to 4 times the heat of water for its size. That is what lets a unit the equivalent of an 80-gallon cylinder shrink to roughly a quarter of the footprint and tuck under a stair or onto a countertop. That density does more than save space. There is almost no standing loss, because the energy sits in cool, solid salt instead of a tank of hot water steadily leaking warmth. So daily losses fall to around 0.5 to 0.77 kilowatt hours, against the cylinder's 1.3 to 3.3. The battery holds under 4 gallons of actual water at any moment, all of it moving through the exchanger on demand. That means there is no stagnant store for Legionella bacteria to grow in, and no need for the regular high-temperature purge cycles a normal tank requires. And you can charge it from whatever is cheapest, an overnight off-peak tariff, surplus solar from your roof, a boiler, or the heat pump itself, melting the salt when power is cheap and drawing it down when you need a shower. All of that capability has to be weighed against what it costs, and set against a traditional cylinder, the obvious gap is price. A standard tank might run between 1,200 and 2,000 pounds fitted, while a Thermino equivalent to an 80-gallon cylinder lands around 4,300 pounds installed. That is a real premium on day one, but it narrows once you account for what the cylinder quietly costs over its life. A tank over 4 gallons falls under UK building regulations called Part G3, which means a certified installer, a pressure relief discharge pipe, and an annual safety check for as long as you own it. The battery holds less than 4 gallons, so it sidesteps that regime entirely, with no discharge plumbing and no yearly sign-off. For a social landlord running thousands of homes, that exemption alone is a serious saving. The more interesting comparison is against the other modern option, the heat pump water heater, which is a small tank with its own built-in compressor pulling warmth from the surrounding air. Those are efficient, but they are bulky. They need clearance and airflow around them, and installed they run far dearer, with figures of 8,750 to 12,500 pounds reported once site complexity is added. They also still store a tank of warm water, so the Legionella cycles and the standing losses come back with them. The battery's pitch is that it gives you the compactness and the safety without that mechanical box. There is also the option of just keeping a cheap cylinder, and for a home that already has the space and a working tank, that may well be the rational choice. The case for the battery is sharpest, exactly where the cylinder fails. A home with no room for a tank, or one chasing a heat pump retrofit that the space problem would otherwise kill. The reason this is landing now rather than a decade ago comes down to a shift in how homes are heated. Governments across the West are phasing out gas boilers to hit net zero targets, and the UK's Future Home Standard is pushing low-carbon heating into new builds. That means millions of those combi boiler homes with no tank are heading toward a heat pump and the storage problem that comes with it. A battery that fits where a cylinder never could turns a structural headache into a cupboard-sized job. At the same time, the economics of running these homes have got trickier. There is a wide gap between the price of electricity and the price of gas, often called the spark gap, that can make a straight switch to electric heating more expensive to run. The way around that is to charge when power is cheap, and time of use tariffs like Octopus, Agile, or Economy 7 now let you do exactly that, buying energy at its overnight low. A store that loses almost nothing while it waits is far better suited to holding that cheap energy until the morning peak than a leaky tank that gives much of it back to the cupboard overnight. And for blocks of flats, there is a third pressure. New rules like the UK's Heat Network Assurance Scheme are clamping down on the heat lost in communal systems, where old central tanks and constantly circulating hot water can shed more than half their energy in the pipes. Putting a small battery in each flat lets the building drop those hot loops entirely and send round only low-temperature energy to charge each unit. That is one of the few ways to actually meet the new limits. For all that, the technology has real ground to cover before it becomes a default, and the obstacles are honest ones. The first is physics. Salt hydrates like this one conduct heat poorly. So during a long heavy draw, a fast shower running the battery hard, the salt nearest the exchanger freezes solid and forms an insulating crust that slows the heat coming out behind it. The water temperature can then start to sag. Getting around it means building conductivity into the salt itself, blending in materials like expanded graphite to move heat faster, and how well a given unit holds up under sustained demand is the thing to watch. History is a fair warning here too, because heat-storing salts have failed before. Back in 1948, the engineer Maria Telkis built a solar house in Massachusetts heated by a similar salt, and it collapsed within 3 winters as the salt separated out and stopped holding its charge. That exact failure, the salt splitting into layers and losing capacity over a few hundred cycles, is what killed the idea for decades. It is the problem the Edinburgh chemistry was built to fix. Sunamp's answer was a set of additives that stop the salt separating and force it to freeze predictably, validated by watching it cycle under X-rays at the UK's national synchrotron. The company now reports holding more than 95% of capacity past 40,000 cycles, the equivalent of more than 50 years of daily use. That is a strong claim, but it is still largely a lab and warranty promise. What would fully settle it is decades of these units running in real homes without fading, which by definition nobody has yet. The last hurdle is people, rather than hardware. The plumbing and heating trade is not yet fluent in this kind of kit, and field reports describe untrained installers, faced with a complaint, simply flipping the system over to expensive direct electric heating and wiping out the efficiency the battery was bought for. Solving that means certified training and pre-packaged systems that are hard to set up wrong, which the company will have to scale alongside the product. Even with those caveats, the direction of travel is clear and the money is lining up behind it. The company has taken a £20 million investment from the Scottish National Investment Bank to scale production at its East Lothian factory and expand into new countries. And in 2025, it brought in a new chief executive, Grant Richardson, to run that growth phase, while co-founder Bissell stepped back into an advisory role. The manufacturing footprint is widening fast. There is a new factory partnership in China for the Asia-Pacific market, and a deal to set up production in California for North America. All that alongside integrations with major heat pump makers like Mitsubishi and Haier, so the battery works neatly with the systems people are actually buying. On the ground, the real-world trials are already running, including a Scottish project that put more than 700 of these batteries into 625 social homes, and a tower block retrofit that paired them with heat pumps and cut tenants' weekly energy bills by 67%. If you are watching this from outside the UK, that North American production line is the signal worth tracking. Availability is only just beginning to spread, and by the time it reaches you, the technology will have several more years of field data and cheaper, faster discharging salts behind it than the units going in today. Strip it back, and what Sunamp is really selling is not a better tank, but the end of the tank as a thing you have to find room for. It turns the biggest physical barrier to getting a home off gas into a box that fits where the old cylinder never could. The upfront price is still steep, and the long-term durability is still a promise, waiting on real-world years to confirm it. But the falling losses, the tightening rules, and the serious money behind it all point the same way. I hope you enjoyed this video, and if you want to stay ahead of where home energy is going, subscribe and stick around, because we will keep covering the most interesting developments in home technology as they arrive.